My talk is based on a note on smooth affine SL2 surfaces by Freudenburg. And before I start, let me introduce some notations that we will use throughout the talk. Our ground field is denoted by K. Okay, I will try. Characteristic of this field is 0. This field is algebraically closed, and we denote by D an algebra, a polynomial algebra in 3 variables modulo the ideal which is generated by this polynomial. And let Y be the corresponding variety to D. Let R be the algebra of the two invariants of D, where the 2 acts on D by the following rule. The 2 is isomorphic to the group generated by mu, where mu of xi is equal to minus xi. The aim of the talk is to prove and show some properties of oh, well, I've forgotten to write the main character of my talk. Variety x is the corresponding variety to the algebra R. And the aim of the talk is to discuss and prove some properties of X, which were obtained by Freudenburg in his note. There are 4 main results, and we will prove the first result in detail, and then comment on the rest of them. And the plan of my talk, which I will try to follow, is the following. Firstly, I will prove that X and Y are homogeneous spaces for SL2. Then I will state the first theorem, then introduce the necessary definitions and lemmas that we will need to when we prove this theorem. Then I will prove the first theorem, state the second one, and then state the third and the fourth one. Okay. Firstly, we are trying to prove that X and Y are homogeneous spaces for SL2. Define xi from SL2 by the equation and T, one-dimensional torus in SL2, which is defined by then denote by K the group generated by Xi, and note that this group is isomorphic to Z4. And denote by N.
Ananya, do you understand what is Z4? What is this? Because usually internationally this is denoted as Z mod 4Z. But in Russia we use notation Z4.
And N is a normalizer of the torus in SL2. Then N and T are the only closed one-dimensional reductive subgroups of SL2. And by Matsushima's criterion, which claims that if we have homogeneous space J modulo H, where J is affine reductive algebraic group and H is a closed subgroup of G, then this homogeneous space is an affine if and only if H is reductive. Then
It's better to write down.
okay. Then by this criterion, we have that homogeneous spaces SL2 modulo T and SL2 modulo N are affine surfaces.
Just a short note, I'm sorry for interrupting, but this was the aim of my talk which I gave in October, I don't remember, to explain this business with quotients. So this statement that if H is reductive, then the homogeneous space is affine, this is basic. This is just because reductive group H acts on the variety G by right multiplication, and quotient by reductive group is always affine. This is basic. Non-trivial part, what Matsumura proved, this is another implication. That if this is affine, then H is reductive. So what you use, this is not Matsumura criterion, this is a basic.
Okay. Let X, Y, Z, W be coordinates for SL2 and X, W, minus Y equals 1. And let B denote its coordinate ring. The actions of T and N on B are given by the following. And therefore, T invariance of B is equal to K of W, X, Z, Y, Z, with the equation above. Now set A as XW, B as XZ, C as YZ, and D as YW. Then A is equal to C plus 1, and BD is equal to C multiplied by C plus 1. Then if we put B tilde minus fourth root of 2B, D tilde fourth root of 2d and a tilde I fourth root of 2 minus square root of 2a plus 1 over square root of 2. Then
Do you want to identify these homogeneous spaces with x and y?
yes, we are trying to prove that x and y are homogeneous spaces for SL2. Then we see that 2b tilde d tilde minus a tilde squared is equal to 1. And since that T invariance of B is isomorphic to G. And then
Well, if it's not difficult for you, write down, you have y equals spec G, right, continue this. This is SL2 over
I'm sorry.
Y equals to homogeneous space. So SL2 modulo 2.
Oh, okay.
And for x you can
Mm-hmm. And for n invariance of B, we have that it is equal to K invariance of T invariance of B. And since let's C prime B C plus 1 over 2. Then T invariance of B is equal to K of B C prime D. And then since psi acts on B C prime D like minus B minus C prime minus D, we see that this algebra is isomorphic to K over Z2 invariance of BT. And in turn, this is isomorphic to Z2 invariance of D, where the 2 generated by mu. And this is our R.
I don't understand. The algebra B to the equivariant is dimension 3 or not?
No, B is dimension 3. There is an equation.
Determinant.
Determinant equals to 1.
But
BT
which is the second one? What is the second one?
No. B is 3-dimensional and T invariants are 2-dimensional.
Okay, I see what Sasha means. Sasha means that BT is written, so it is generated by 4 elements modulo 1 relation. But certainly this is not the only relation between this.
Of course, product of 2 of them equals to product of another 2.
Okay.
Mm-hmm. And hence we have that X is isomorphic to homogeneous space SL2 modulo N. So X and Y are homogeneous spaces for SL2. And now I will state the first theorem.
Oh, Polina, just to ask you. Okay, erase it and then we'll ask. we have SL2 over T, SL2 over N, what else?
Affine plane.
Affine plane is not homogeneous space.
You said that these are all the two-dimensional homogeneous spaces.
No,
Affine.
no,
Affine.
no, affine. No, but we can divide it into some types. So the smallest homogeneous space, certainly this is a point. One-dimensional homogeneous spaces. What are one-dimensional homogeneous spaces?
Equation about two-dimensional subgroups. Do you know some two-dimensional subgroups?
Firstly, dear students, not graduate students, but students, help us. What are homogeneous spaces of SL2?
That was somehow discussed in our seminar in Moscow State University last year.
This is written in graph book. What is a one-dimensional homogeneous space of SL2? P1, but as a homogeneous space, what is this? SL2 over, so let us write down SL2 over B, isomorphic to P1. And one can check that this is the only one-dimensional space. You cannot construct any finite extension or no other two-dimensional subgroup, nothing. This is the only. Now we come to dimension 2. We have SL2 over T, SL2 over N, what else? Who knows? Not only students. Just raise your hand. Who knows? Anton knows. Sasha knows. Roman knows because he doesn't know. Sergey, do you know?
Yes.
Who else? Ivan, do you know? Okay, the youngest maybe is Anton. Okay, Kirill. Sorry? No, there isn't any. Yulia, do you know?
But my suggestion is to discuss such things when others give a talk. He don't like this because he have limited time. So
No, but
let's discuss this.
No, but okay.
GA subgroups, right?
Anton, tell us, what will be the answer in two dimensions?
Well, as a quotient space. Well,
As a quotient space, it will be SL2 over what?
we have a group triangular matrices, and on diagonal 0 dot unity, one blank space and some elements.
So, can you write down U, capital U, and this index n? By definition, this is the set of matrices, 2 by 2 matrices. Epsilon, A, 0, epsilon minus 1, where epsilon power n.
minus.
Where epsilon power n equal 1. And A is arbitrary now. Equal 1? 1 for 1. And A belongs to R2. And how do we imagine what is the SL2 over UN? Write down SL2 over UN. Sorry? No, everything is good. So what do you do? Everything is correct. So what is it geometrically?
It's affine plane without point, quotient by.
Okay, write down A2 minus origin. And then quotient by cyclic group Dn. Okay, and very quickly, what are three-dimensional homogeneous spaces?
So 2 divided by a finite group.
Okay, let us write down. will not waste time, but this is very easy to list all kinds of subdependencies. So this last type, they are all affine. And this previous time, SL2 over UN, they are not affine. So they are all quasi-affine. Okay? Okay, so sorry for interrupting, but this is a basic education, you should know.
Now I will state the first theorem.
Maybe to erase this, to have full lecture.
Okay. Well, let X be equipped with SL2 action defined by its structure as a homogeneous space for SL2. Defined space of dimension 5 is equipped with SL2 action which is induced by the irreducible SL2 module of dimension 5. And A4 is equipped with any algebraic SL2 action. Any.
And the first one is irreducible.
Yes, and you will
Yes.
Not maybe I don't, irreducible. Or, the second one.
Okay. Then we have 5 points that hold true. There is an equivariant algebraic embedding of X into A5. There is an algebraic embedding of X to A4. There is no equivariant algebraic embedding of X to A4. There is no algebraic embedding of X to A3. And the cylinders are not isomorphic as algebraic k-varieties. Actually, this theorem shows an example of non-extension of action, group action on X to A4.
So there exists such actions.
No. X and Y is like 0.
Okay.
X and Y are this X and Y.
And this also given the actions on A4 F5.
On
And
A5, this is the only reducible five-dimensional
yes.
representation.
And for F4, there is no equivalent for any action.
So for any action on A4. Okay.
So SL2 action on X doesn't extend to A4. Examples of such non-existing of extension for other groups were known before, but for SL2 it seems to be the first example. And to prove this theorem, we have to make some definitions and state some lemmas that we will use in the proof. Suppose that B is define codomain. And on this set of derivations of B, this set can be viewed as a Lie algebra with usual bracket operation. Then we define for two locally nilpotent derivations D and U. We say that this pair is a fundamental pair for B. If B and D and U satisfy the following equations. That is, D and U generate a Lie subalgebra which is isomorphic to Lie algebra of SL2. Then we set H, which is equal to DU, and then note that U, D, and H is an SL2 triple.
Write it down. 3 elements are SL2 triple. So Freudenburg used term fundamental pair, but I would prefer SL2 triple.
But we will, in our further discussion, we will use just D and U. So it's more convenient to say that it's fundamental pair, and
These are two nilpotent elements, and this is
Yes.
and H is missing.
The order is so the order is exactly that.
yes.
I'm very sorry, but short comments about formulation. So look to item B, to assertion B, statement B. This is funny because you have, what is X? X is a surface which is given by one equation. This equation is written in 3-dimensional vector space. Okay? So this is D. The variety is Y and algebra is B. Yeah. So it shows that Y is surface, in particular hypersurface, in 3 dimensions. Now you take an action of a group of order 2 by this minus, okay? And you have an algebra of invariants. And you may compute easily that there are many basic invariants and then satisfy many relations. So this is no longer hypersurface. But it's not clear, because maybe you can find other system of generators such that it will be a hypersurface. So this is of dimension 2, so maybe you can find 3 generators and it will be only one relations among them. Okay? This is smooth because it is homogeneous. So point D says that this is not hypersurface. And we will see it's very interesting how to prove it. Okay?
Well, H is a semi-simple derivations, and it induces a Z grading of B. Note that D and U are homogeneous with respect to this grading, and the degree of D is 2, degree of U is minus 2. Then let A be the kernel of D, and then A is a graded subring of B. And in addition, A0 is equal to the intersection of the kernel of D and the kernel of U, which is in turn is equal to SL2 invariance of B. Okay. B is an arbitrary affine codomain. If we have F is in AD, then define a vector space with the basis UGF. We will need it later. And finally, set Vn the irreducible SL2 module of dimension n+1.
And what are these x's? Direct sum of what?
It's just generators x0, xn.
Just a basis?
Yes.
Okay, and what is this gradient? This is arbitrary gradient of So this is a gradient by h.
Yes, I
H is
have said it. Yes. And Vn induces a fundamental pair Dn Un, which is defined by the following. Okay, then we need the lemma. Let f1 dot fr be non-zero and homogeneous elements of A. So fi is in ADI, such A is the kernel of B, such that A is equal to K of F1, Fr. Then B is equal to K of F1 hat dot Fr hat, and moreover there exists an equivariant surjection phi from module 2b.
F hat, this is not an element, this is a vector space.
Yes, this is a vector space. This is just a notation. Okay, and now we define fundamental. Yes, I will not prove. Yes, I will not prove the lemma. SL2 action. Yeah, now we define fundamental pairs for D and R.
So this lemma is an exercise.
Yes. Okay.
If you are going to prove it, don't erase it.
I will remind every point of this theorem. Okay, we have k of v2, which is equal to k of x0, x1, x2. With a fundamental pair d2 and u2, which are defined as the above. Then we see that the ring of invariants under SL2 action is equal to k of 2x0, x1 minus x1 squared. And then let delta prime v prime be the induced fundamental pair on D. We see that action of Z2
What is D?
is from the beginning our algebra.
And in which sense it is induced?
Well, since SL2 invariance of this algebra is like that, we can say that D2 and U2 they preserves this relation, and then we can induce this fundamental pair. And, no, yes.
And this minus 1, it doesn't matter.
Yeah, it doesn't matter.
So we just restrict this derivation to the subalgebra.
No, not to the subalgebra. To the quotient algebra. So you say that the ideal generated by this element is invariant, so we have an inducement of the quotient. Okay.
And since delta prime and v prime commutes with that two action, we see that this fundamental pair restricts to R. Thank you. Okay, and
Because they compute with this Z2 action.
yes. Now we are ready to prove the first theorem. In the first part of this theorem, we are trying to prove that there exists an equivariant embedding of X into A5. And since we have delta and V fundamental pair on R, then we have that R is a Z-graded ring. And let A be the kernel of delta.
This gradient is again given by H.
Yes. Note that R can be written as K of x0 squared, 0x1,
Of course, with some relations, but
yeah. Then let's change coordinates in R. Let x0, x2 plus x1 squared be instead of x0, x2, and 2x0, x2 minus x1 squared be instead of x1 squared. The matrix of this change is invertible, so we can continue the equation. And we see that this is 1, according to definition of R. So we can rewrite it and just remove. Then the action of V on R is given by the following. And hence we see that R actually equals k of x0 squared hat with accordance with this definition. And then, since the degree of, since x0 squared is from R4, where R4 is the component of this decomposition, this yields that by lemma there is an equivariant surjection phi from k of V4 to R.
Can you tell us in general what you are doing
now? Now we have just proved the first part. Since we have an equivariant surjection phi, which we obtained by this lemma, and hence there is an equivariant embedding of x to A5. And this is the end of the first part. Mm-hmm. Part B. In this part, we are trying to prove that there is algebraic embedding of x to A4. And to prove this part, we need the result of Benzmann and Makar-Limanov. They realized x as a subvariety of A5. Namely, x is defined by the ideal in the algebra in 5 variables. By the following 6 polynomials. Moreover, one can see that the following equation holds. And this is again from J. So x can be also realized as a subvariety of A4. To be more precise, let's put P x u minus yt, and then the ideal in J tilde in algebra in 4 variables. Define x and J tilde is y squared and so on. So we just write p instead of z and have a realization of x as a subalgebra of A4. So there is an algebraic embedding of x into A4. And it completes the second part. The next part C. In this part, we're trying to prove that there is no equivariant surjection of x into A4. Let D4 and U4 be a fundamental pair on K of D4, where D4 and U4, as we have defined earlier. Here. Set A tilde is the kernel of D4, and again is a graded subring. In algebraic theory of local and nilpotent derivations by Jean Freudenburg in the 8th chapter, it was shown that in this case A tilde is equal to K of x0 f g q r, where q are from A0 tilde, x0 f are from A4 tilde, and g is from A6 tilde.
It's not clear what I do now. You prove that x cannot be equivalently embedded into a reducible 5-dimensional model.
No.
Or you say
Four-dimensional model.
No, this is some preparation.
It's some preparation for, yeah.
Because this space is 5-dimensional.
Yes. Then we see that AD tilde is 0 for odd D, and for D which is equal to 2. From the proof of the first part, we obtained an equivariant surjection phi from K of V4 to R, and then we have that AD is equal to phi of AD tilde. Hence, it follows that AD equals 0 for odd D, and D which is equal to 2. Moreover, note that A0 equals K, and it will be condition star. Okay. According to Panishev, every algebraic SL2 action on A4 is equal to the action induced by SL2 module in some coordinate system. There are
To punish us, please prove linearization problem for semi-simple group acting on 4-dimensional spaces.
There are 4 non-trivial SL2 modules of dimension 4. Namely, they are V3, V1 plus V1.
Equivalent. This conjugation of
Okay, we will prove this part by contradiction. Assume that there is an equivariant embedding of X into A4. Then there exists an equivariant surjection K of W to R. Where W is one of those 4 modules listed here. Let's let D bar and U bar be the fundamental pair on K of W, and as usual, A is the kernel of D bar. Well, the first case. Assume that W equals V3. According to the same 8th chapter of algebraic theory of local and important derivations by Freudenburg, we have that in this case A bar equals K of X0 FGH, where H is from A0 bar, X0 G is from A3 bar, F is from A2 bar, and moreover X0 squared H equals F cubed plus G squared. By our condition star, we have that A3 is a psi of A3 bar, and it equals 0. A2 equals psi of A2 bar equals 0. And psi of H is from A0, which is equal to K. Hence, since A is equal to psi of A bar, we have that it is a subalgebra of K, which is a contradiction. So this case cannot occur. And we can prove cases for the rest of these modules in the same manner. So I will skip this part. And since any of these cases cannot occur, we see that there is no equivariant surjection from K of W to R. Hence, there is no equivariant embedding of X to A4. And this finishes the third part of the series.
So this is some analysis of SLT module structure to guesses as a specific system.
And since we don't have much time, I will skip the proof of the fourth and the fifth.
No, this
part.
is better just, we want to know about this hypothesis. Just tell us the idea of this scheme.
Okay. Yes, I can. I can. Well. In this part, we are trying to prove that there is no algebraic embedding of X to A3.
As to me, this is the most interesting.
That is not most important that you cannot list the action from a subvariety to the whole affine space.
It's clear. It is clear which technique to use to prove that X is not equivariant embedding in A4. Just analysis of this model structure. And here I don't know which technique to use.
Okay.
Okay. Well, since X is a homogeneous space for SL2, it follows that X is smooth, and moreover, we have the following. And hence, the Makar-Lemanov invariant of R is equal to K. Flanner and Zeidenberg proved that X is not isomorphic to hypersurface of the form xy equals p of z, where p of z is from k of z. On the other hand,
They prove it using Makar-Lemanov invariant.
No.
Or
No.
this concrete hypersurface is not isomorphic.
this concrete hypersurface is not isomorphic to.
Makar-Lemanov of this hypersurface is K also, so it can be proved by Makar-Lemanov.
On the other hand, the condition for a smooth affine surface with the Makar-Lemanov invariant of R of this which is equal to k, to be isomorphic to hypersurface of such form, is equivalent to the condition for such surface to be isomorphic to a hypersurface in A3. So this implies that X is not algebraically isomorphic to any hypersurface in A3.
So conclusion, the proof of point T comes from other results. But let us list this result.
And yes, the first you said, this is result due to Kahneman.
Flenner and Seidenberg. And the second, the condition for a smooth affine surface with the Makar-Lemanov invariant, which is equal to k, to be isomorphic to such hypersurface, is to be isomorphic to a hypersurface in A3.
Who proved it?
I guess Freudenberg, he didn't mention it, actually.
Every hypersurface in A3 with trivial Makar-Lemanov is this one, right?
Yes. Yes.
It seems that there is a paper due to Makar-Lemanov about surfaces with trivial Makar-Lemanov invariant. Maybe this is the result of this paper, but I'm not sure.
Okay, so direct arguments are not direct.
Yes, maybe the main part is this one, that X is not isomorphic occasionally.
Okay.
And I will not prove the last part. I will just go on and state the second theorem.
The last part was about Freudenberg.
Mm-hmm. And to state the second theorem, we have to list some definitions. Firstly, for an affine codomain B, and for D, which is D on B, the Plain's invariant of D is the intersection of the kernel of D and the image of B. Let K on D of B denotes the following set. say that D is an irreducible LMD of B if D is not contained, if the image of B is not contained in any proper principal ideal of B.
Sorry, what is the condition?
Yeah.
It's a collection of subalgebras. And what is 3, I don't understand.
We say that D is irreducible LMD.
If its image is not contained in a
In-
principal idea.
Any proper principal idea.
Okay.
Then we say that B has transitivity property. If the action of the group of automorphisms of B on this set is transitive. Then we say that B has strong transitivity property.
It's actually stronger.
If the action of this group on the set of all irreducible LMDs is transitive. And the last definition, assume that B has a strong transitivity property. Then we say that the plinth invariant of B is the isomorphism class of kernel G modulo plinth ideal of D, where D is irreducible.
This full, this is the ideal in the kernel.
Yes.
Mhm.
So this should not depend on you. So this is an equivalence class.
Yes,
Because
yes.
of this property.
And the second theorem claims that R has the strong transitivity property. And its plinth invariant is K.
Okay, this even invariance is not so impressive, but strong transitive property is so nice because it says that there is somehow only one locally important derivation, all other are equivalent. Certainly they are maybe irreducible or not irreducible, and they are not equivalent, but all irreducible are equivalent.
I don't agree about Polina's invariance because they use these invariants to prove the next theorems.
Okay. We will be impressed by the next year.
Yeah. But okay, I will not prove it. And to state the third theorem, we have to define some subgroups of the group of automorphisms of R.
And this variety X, this is definitely flexible because this is a homogeneous space of X. So we have many LEs because we have this infinite entity. But this is fun is that essentially there is only one element reducible and all other are good.
This idea invariant equal to 3 doesn't mean that it specifies equivariant.
Maybe not. Because it will have a slice and it will be decomposed into the rest product.
Yeah.
So it's going to change it.
If this idea equals then it contains one.
The factor, the quotient is k, so it's not trivial, but k, so Prince ideal have dimension 1. I believe that kernel is equivalent something like polynomials in one variable, and Prince ideal is something like
Okay, we use these notations for the subgroups of the group of automorphisms of R. T is the torus in PSL2. E is such group where where delta is the restriction of delta prime as we have earlier defined it in the proof of the first theorem. T tilde is a group generated by E and T, and H is the intersection of PSL2 and T tilde.
And maybe not to erase this, you don't leave this plan
Yes.
of this. Do you understand why we have PSL? Because SL2 acts on this X non-effective. Effective action is by PSL.
And third theorem.
December, I know.
The third theorem claims that the group of automorphisms of R is a subgroup of the automorphisms of D, which consists of elements which restrict to R. And the second part claims that this group is isomorphic to amalgamated product of PSL2 and T tilde. Yes.
the conclusion of this is that we have an interesting, flexible, smooth surface, not hypersurface in S3, and we have explicit description of the automorphism group. And moreover, this automorphism group is an amalgamated product. So this is amalgam.
And this amalgamated problem is very similar to amalgamated product in the case of affine plane. So this tilde is just like triangular.
And PSL2 is like
a fine.
And finally, the fourth theorem. Define a polynomial and define R tilde is R of S modular ideal generated by F, and let X tilde be the corresponding variety. Then we have that the cylinders are isomorphic, but these varieties are not isomorphic. So this is the counterexample to generalized cancellation problem. And the proof of this theorem uses this length invariant. Yes. The Plains invariant. They count Plains invariants and in part B. Yes. So we have to finish, I guess. And
What about the proof of A?
yeah, we have to use. If you remember, in the proof of the first theorem, we said that R can be viewed as some algebra with some equations, something like that. And we should use this representation to prove the first part. It is easy, but it's just technical.
Is it related to the last part that you mentioned?
No.
This is just this is isomorphism just given explicitly, or some technique?
Some technique calculations.
Does he use slice theorem or not?
Yes.
I have a comment about the theorem 3 item B. We have this amalgamated product. We have PSL2 instead of affine transformations when the cook theorem, because we have something fixed that kills the translation part. This is something fixed. Can be seen from the Plains ideal. Plains ideal to the Plains invariant with K means that there is a unique affine line consisting of 6 points. I guess so. This somehow kills the.
I'm not sure, because this is this K can be different for different LMDs. This is after isomorphism. It's rather strange if this K is the same. I don't know.
Okay, good point. Maybe it's dangerous. Okay.
So do you understand the proof of all theorems?
Yes.
So you studied completely
Yeah.
the proof of all theorems. And Veronica thought will be a continuation of this. Because the next paper of Freudenburg participated on the same subject.
do we have example of affine surfaces with some bad automorphism group, which is not algebraic, American product of algebraic group and some nested loop of the group?
In theory, there are isotonic surfaces when we have something called a graph of groups. This something bigger than megametric product. If you see megametric product as a tree of groups, then this graph of groups is not no longer a tree. So it's not a megametric. It's something bad with cycles.
Take a torus. What is the automorphic group of a torus as a group? Well, the connected component of D.
And this one, example, component, for example, future automorphic